Hello there, everyone. My name is James. I am a licensed practicing pharmacist, and welcome back to Pharmacy for the People, where I try to put your health back into your hands by taking complex pharmaceutical ideas and breaking them down into bite-sized morsels. Today, we're going to cover something that's really important for almost every medical decision that a pharmacist, a physician, a nurse, a surgeon, etc. makes. And whether it's intentional or not, the question I'm about to ask heavily influences the decisions that we make as patients too. So I'd recommend starting on this video before tackling any other videos about the complexity and the legitimacy of medicine. The conclusions we arrive at on this issue influence almost all the others. Is medical science trustworthy? Can you, for yourself and for the people you love, trust what experts are recommending? Right off the bat, this is a hot button issue. A big, ugly elephant in the room, right? With growing groups of people questioning the legitimacy of vaccines, questioning how we have or should have responded to the SARS-CoV-2 virus, a growing industry of homeopathic and alternative medicines, the occasional gaslighting demagogue intentionally working to undermine trust for personal gain. The divide between health professional and patient seems to be ever widening. I dare say that all of us in the healthcare industry and outside the healthcare industry have the same goal: to enjoy life with the people that we love without making unnecessary sacrifices. Sacrifices like spending a whole lot of money or not being able to enjoy the things that we like to eat or do or have fun with. Really consider that. Regardless of worldview, ethnicity, background, education, etc., we have this in common. That should be unifying. So this growing divide, make no mistake, it's not a matter of understanding versus lack of understanding versus background versus perspective. This is a trust issue. Healthcare in America is rife with issues. People have been hurt. People have been lied to. People have been offended. There has been a loss of trust. Neither side is without blame. I won't point fingers. Instead, I just want to start with the rebuilding process. Reconciliation. That was a major driving factor for why I wanted to start this channel. I want to rebuild trust between the patient and the healthcare professional. I can't tackle all of the elements involved in this at once, but I think a really good place for me to start is with medical science. Let's start with this one issue and break it down. What is science? Medical science is a complex issue, and trustworthiness is even more complex. So just like with any complex issue, in order to arrive at concrete conclusions, firm conclusions, we need to break it down to the basics. So let's start with science in general, and then see how it applies to medical science. Science of any variety is a systematic method of investigation. It is not a system of belief or a worldview in and of itself. So for all of you out there whose worldview includes faith and spirituality, neither this video, this pharmacist, nor science itself is in opposition to your worldview. I'll justify that a little bit further later, but for now, please don't tune me out because I used the S word. Science, including medical science, is a method of investigation. It's also called the scientific method. It's comprised of a few parts. You have a question, a hypothesis, a test, an analysis, and a conclusion. Generally speaking, this is how most of us arrive at conclusions anyway. So why do we need a system? Delineating it into a process helps us to eliminate as many errors in our methods and conclusions as possible. And there is a huge opportunity for error here. We observe and conclude without taking the whole picture, the whole process into account all the time. For instance, we mistake correlation with causation all the time. A false cause fallacy. We think that touching a light switch is what causes lights to come on. We think that wearing our team's colors is what causes our team to win. We think that I've never gotten sick because I always drink elderberry tea. It doesn't mean that these things aren't related or correlated, but it does not establish a clear causal relationship from one to the next. This is a very important concept, and it can be applied very widely. There are things called confounding factors. These are elements that we may not have been able to take into account in our initial observation and conclusion drawing. For instance, with the light switch, electricity is a confounding factor. If you don't understand how electricity works, you may be tempted to believe that touching a light switch causes the lights to come on. But we know that's not it. It's not our hand moving this thing. It's turning on a circuit that allows electricity to flow to a light bulb, and the light comes on. With team colors, it's chance versus complex motivational factors. That's the confounding factor there. When I was first training as a pharmacist, I had a couple pharmacists that were wiser than me tell me that you don't know what you don't know. That is, you are unaware of your ignorance. I think that applies very well to a lot of our casual conclusion making. A method or a system can help us to tease out these common mistakes. So let's apply the scientific method to an example in medicine and see what kind of errors come up. In our example, our question will be, will gas X or simethicone reduce stomach pain? Our hypothesis or hypotheses will be, the null hypothesis will be simethicone will not reduce stomach pain. Our alternative hypothesis will be simethicone will reduce stomach pain. Don't be confused by the null and the alternative here. The null hypothesis just means that the two things are equal. The alternative means they're not equal, relatively speaking. It's just jargon. For our test, we will just take a dose of simethicone every time we have stomach pain and record the results. Our analysis, 7 out of 10 times, I didn't notice any difference in stomach pain. And so our conclusion is simethicone does not reduce stomach pain. This conclusion sounds very reasonable at first, but when we start picking it apart and looking for errors in the way that we've conducted our study, our conclusion falls apart very quickly as any concrete form of evidence. Let's start with the question. Will simethicone reduce stomach pain? It sounds like a very reasonable question, but is the question specific enough to find a specific answer? For instance, are there different kinds of stomach pain that might be involved? Stomach pain from heartburn, from gas, from stomach cancer, from sutures that have torn out after a bariatric surgery. The question could be restated as, will simethicone reduce stomach pain associated with bloating or associated with spicy foods? The more specific you are, the more specific of an answer you can find. The hypotheses really only exist to clearly state what we're trying to find out. Either the null hypothesis, that the two things are equal and simethicone does nothing, or the alternative hypothesis, simethicone will work. Methods of testing are a big area of issue here. Good trials are designed to eliminate as many confounding factors as possible. Remember, confounding factors are those things that we don't take into account when we're casually observing a relationship. Is your own stomach pain experience similar to someone else's, or is your stomach pain unique? Were certain foods involved at different times? Were any other therapies involved that you didn't write down explicitly? Is there biodiversity at work that may explain why simethicone works or doesn't work for you in particular? If you've only tested your hypothesis 10 times, have you actually tested it enough to find the difference between a coincidence and reality? Is there a control arm on your study to guard against coincidence? Placebo is needed to show the difference between the effects of the medication being tested and the effects of coincidence. In our example, we've found a negative result, right? We didn't see any difference. But what if it was switched around? What if we said 7 out of 10 times we did see a resolution in stomach pain whenever we took simethicone? But if we didn't have a placebo, then we don't know how much of that was simethicone and how much of that was nothing. A placebo would enable us to answer the question, are the results more or less impressive than nothing? Very briefly, a placebo is something that would look exactly like the thing that we're testing, and the person taking it would not be able to tell the difference. They would be blind to whether they're taking nothing or actual medication. It helps to eliminate bias. Analysis. This is another really big opportunity for error. We are finite creatures who are only able to observe in very small bits, but we love to take those small bits and apply it across a huge range. That's called generalization. And hasty generalization is one of the biggest issues that we face when we're doing our analysis. We apply a small set of data to a really big group of people. In our example, we have a sample size of 1. If it was me in the experiment, the demographics that our experiment would apply to would be 35-year-old white males who live in Virginia who are me. So could I apply those results to a 68-year-old black woman? Could I apply those results to 14-year-old Hispanic males? Could I apply those results to 35-year-old white women who live in Virginia? Now, you might be tempted to say yes on the last one, but it's important that we recognize that our data does not support that. It only supports what we've tested. This is one reason why anecdotal evidence is considered very low strength evidence. One person's experience or a couple people's experience should not be applied to a large group lightly. It doesn't nullify their experience, but it also doesn't mean it applies. So you might be asking yourself, how do you design a trial that captures all major demographics? Or how do you get enough people in your study to generalize to the whole? Well, the answer is you don't. It's not financially feasible, and most of the time it's just impossible to gather everybody in a demographic. I can't get all the 35-year-old white males that are in Virginia in one place at one time to run a test. So you limit your field, you capture the demographics that you capture, and then you turn to inferential statistics to see if it applies to a larger group. Inferential statistics. I don't want to beat you over the head with data, methods, jargon, statistical analysis, etc., but I feel like I have to give you at least a peek into how the sausage gets made so I can help you to understand this process. We use inferential statistics to evaluate the probability that our results reflect reality. What does that mean? Think back to our example earlier about the number of times we tested our hypothesis and the number of people we tested it with. We tested it 10 times with one subject. We don't have to assume that this was too little testing and too small of a sample size for a conclusion to reflect reality. We can calculate the likelihood that our conclusion is an error and show the sample size was too small. In medical studies, we generally accept an error rate of 5%. That is, we, the medical community, will accept your study if you are able to recruit enough people for your study that you only have a 5% chance of your outcome being an error. When I say outcome, in this instance, what I mean is the 70% chance that simethicone will not affect stomach pain. We can calculate, based on factors that are beyond the scope of this video, how many people we would actually have to recruit into our study to make sure that whatever the outcome is, 1 out of 10 times, 10 out of 10 times, 1,700 out of 37,000 times, we can calculate how many times we have to test it and how many people we need to make sure that the likelihood of an error is only 5%. And even then, there are restrictions.
So does that mean that it's possible for the outcome of medical studies to be wrong?
Yes, it does. But a 95% probability of finding a true answer is a very good probability. And I'm leaning on that word probability. I'll bring that back a little bit later. So what about our conclusion? The results or the outcome of the study is distinct from our conclusion. The conclusion you draw from the results of the study. The results are the outcome of the study. So for our example, 7 out of 10 times simethicone did nothing. Those are the results. Our conclusion is simethicone does not help with stomach pain. Bear with me because this might get confusing. Remember, the study only finds data. Conclusions regarding that data can be a source of error. Conclusions immediately draw on the data itself, our prior assumptions made about the circumstances of the data, our personal philosophies, our worldview. Consciously or subconsciously, it can pull on our own cognitive biases and logical fallacies. Cognitive biases are systematic errors in our thinking that cause us to lose objectivity in our judgments. For instance, confirmation bias. Confirmation bias is a bias that causes us to more readily accept a conclusion that already reflects something we believe. So if I, prior to this experiment, believed that simethicone did nothing, and the outcomes of the study were 7 out of 10 times it didn't do anything, what if we only had 5 out of 10 times? So 5 times it did work, 5 times it didn't work, an equal opportunity. If I then drew the conclusion that simethicone doesn't work, it may be because I have a confirmation bias that makes me believe something that I already want to believe. Or the Dunning-Kruger effect. I really like this one, and I super recommend that you look it up. But the Dunning-Kruger effect can cause us to be a lot more confident in our conclusions based on the level of understanding we have in a particular field. If you ever notice that when somebody first starts playing piano, suddenly they feel like they are, Don Concerto. They can do whatever they want to. They're about to become the next great jazz musician, but in all reality, they still haven't figured out what a C minor 7 is. But the further along you are studying your particular field, the more you realize that you don't know what you don't know. The more things you get exposed to, your confidence starts to drop. But of course, as you're gaining more experience and you're learning more, eventually that dropping confidence will plateau, and then your confidence will start going back up as you're actually learning your field. The Dunning-Kruger effect is a cognitive bias, and it's interesting to see that one manifest. Logical fallacies, on the other hand, are errors in the way that we construct an argument. You might see an author use a logical fallacy to defend their conclusion. For instance, a false dichotomy fallacy or a black and white fallacy. That would be in our study is if I said, well, simethicone either does cure stomach pain or it doesn't. But of course, we can say that it might be affected by what we're eating. It could help a little bit. It could help just a smidge. There's a lot of in between. There's a lot of choices in between. It either does or it doesn't. So if your conclusion was that, then you've arrived at a false dichotomy. Or special pleading. Say you were trying to defend that simethicone does work, and that's the conclusion that you've drawn from 7 out of 10 times it didn't do anything. So you say, well, it's probable that the reason that you didn't see any effect those 7 times is because when you swallowed it, it didn't get to your stomach. Of course, you're assuming that the pill is going to get to your stomach. So you're kind of changing the prior assumptions to defend your position. It's special pleading. Suddenly you're moving the field goal. You kick a ball and it doesn't go through, and then you're like, oops, we just moved this forward and now it's a goal. I'm hoping to cover these in a video soon because I think they're really interesting. But they're not strictly speaking related to pharmacy, only to the application of pharmacy. So I'll get there when I get there. It's also important that the conclusions of the study remain within the confines of the study. For instance, if our conclusion was simethicone does not work, therefore meditation is the only way to cure stomach pain, that would be outside the confines of the experiment. We haven't done anything with meditation to test it against the cure for stomach pain. So that would be an obvious overextension of the confines of the study. That doesn't mean that particular conclusion about meditation is false necessarily, but you don't have experimental data to support it. You need to perform another experiment. Let me add a very specific public service announcement that sharply steps into the realm of philosophy, and then I will quickly retreat back to my own field and say, beware metaphysical conclusions that rest on physical observations. Okay, because of these inherent risks when we're drawing conclusions, most clinicians, when they're reading a study, will draw their own conclusions from the data, whether it agrees with the author or not. You can be open to persuasion when you're discussing it with other people, but you come up with your own conclusion. You don't just rest on what the author says. So going through all of that, I hope it reveals a bit about how unsubstantial our initial conclusion about simethicone is. Our question wasn't specific enough. Our test wasn't broad enough. Our analysis wasn't generalizable enough. And our conclusion may not have been fair. So let's consider that a really rough crash course on the nuts and bolts of the scientific method. And let's back up to our original question. Is medical science trustworthy? There are a few points here that I'd like to make that you may not know. Number one, within the medical community, we as individuals, not as a group as a whole, but as individuals, will decide for ourselves if each individual claim made in a study is acceptable. It's not groupthink. If I look at a study and I disagree with the author's conclusions or an author's claim, I don't accept it. And I'm open to discussion, like I said, with colleagues and for them to present evidence and to persuade me. But if I'm not able to arrive there on my own, then just because these other people accept it doesn't necessarily mean that I will. And this is generalizable to a large group of people. We have conversations together where we disagree vehemently about what the appropriate conclusion or action from a conclusion in a study is. Number 2, before a medical study is published, it goes through a process called peer review. Peer review is where the manuscript is sent to other people in the field of study that's being tested, and they look at the manuscript and scrutinize it. They're looking for a lot of the errors that we talked about. They're looking for internal consistency, external generalizability. They're going to pick it apart. Because if it's a good study that supports something that they like, they want it to be a robust study that they can hang their hat on. So then they'll resubmit that back to the original authors to make corrections, or it's possible it'll be rejected outright. If there are enough errors with it, the publisher may just say, sorry, try somebody else. Which means the ability for the authors to get away with bad things is dramatically diminished. For instance, it's required that when you're writing a paper, you're performing an experiment, you have to disclose your conflicts of interest, especially for the funding and your involvement and your allegiances within that experiment. For instance, if I was performing a simethicone experiment, and the manufacturers of simethicone were paying me so that I would do this study, that has to be disclosed. It does not mean necessarily that if a pharmaceutical company is paying for a study, that study should not be considered. It means that you should consider it very carefully when you're drawing your own conclusions, because you want to look for biases that may not otherwise be there. Number 3, conclusions that are accepted are held loosely as more evidence is revealed. Many of the conclusions that were held near and dear 20 years ago have been overcome by more recent studies that are more robust, and they were able to change the opinions of many clinicians and therefore change the course of medicine. In our example, if the next year somebody performed another simethicone experiment and they included 400 people and they tested it 100 times in each person, assuming everything else was okay internally and externally of the paper, we would probably be a lot more willing to accept those conclusions because the study is far more robust. A more recent and maybe sensitive example is that with COVID-19, initially we started off with really small studies because we were trying to find out as much as we could as quickly as we could. And then later, as more larger studies came out, it changed our opinions about certain treatment modalities. And so the recommendations from the medical community changed. Simply put, the conclusions in medical science are usually considered an ellipsis instead of a period. Number 4, the ethical ramifications of producing medical scientific literature that is self-serving, poorly conducted, or dishonest are not taken lightly. There was a physician in the 90s that published a fairly controversial paper, and later it was found out that there was some dishonesty and that he had violated some of the most basic ethical principles of research. As a result, the paper was redacted, taken out of the journal that it was published in, and on review, that physician actually lost his license to practice medicine. He did a lot of damage, and we're still feeling the effects of it. Despite the overwhelming preponderance of evidence contrary to his claims, some people still see his research as the only true voice out there that's telling the truth. Which brings me to the last bit that I'd like to say. We believe many things for other reasons besides robust data. It's important for us in the medical community and outside of the medical community to recognize that. We are human beings with emotions and hopes and fears, desires, experiences, biases. All of that influence what we choose to believe, for better or for worse. We cannot eliminate the human element of trust. Even the most robust, perfectly performed experiment cannot convince a grieving mother not to grieve, nor should it. It's important that we keep medical science in its proper place of importance. The science and medical science is the peddler of observation and probability. It is not the definer of our reality. Remember, science is just a method of investigation. As I mentioned earlier, a 95% chance that your outcomes are not found in error is a very good probability, but it still leaves room to be wrong. If you were to perform the exact same experiment 100 times, 5 out of those 100 times, you may find a different outcome. And you have the right to believe in either the 95% or the 5%. That is your right. You and you alone get to make that decision and face the results of that decision. There is no consensus of the level of evidence required for someone to believe something. That is up to the individual. Keep in mind that your actions and responses to those beliefs may not be your right if they're not provided for by your government, your laws, or your parents. But you may put your faith where you please. In conclusion, number 1, the scientific method helps us to eliminate errors in our ability to observe and come to appropriate conclusions. Number 2, I believe the method of adjudicating medical literature is a trustworthy process that helps to eliminate bias, misleading, falsehood, and self-serving purposes. And number 3, deciding if you believe a claim made by medical literature is up to you, the individual. Having said that, I think it's really important that we continue to defend our beliefs with loving debate, being open to persuasion, taking the whole human into account when we're engaging others. If all else fails, allow the unifying goal of just enjoying life with the people that we love to help to narrow the divide that's between us. Guys, thank you so much for watching this. I really hope that this helps. I really do. The scientific method and scientific literature can be so daunting, and I really hope that this breaks it down a little bit so that you feel more confident in your ability to avoid errors when you're making your own conclusions. I'm going to link a well-written scientific medical paper down in the description. I won't guarantee that it'll be easy to read or that it'll be all-encompassing of all medical literature, but I think it will be a good representative of what a lot of medical literature is like. Hopefully in another video we can dive into how to interpret that literature for yourselves. It will probably be a bumpy ride and a very complex one, but we'll get there. Remember to ask your questions and leave requests for episodes in the comments. Thank you again for watching, and I'll see you next time. Just a fairly controversial paper. My cat, everybody. Hi, Gunter. Come here, you're gonna get on the camera. Yeah, come here. Now, come here. Wow. You wanna say hello? You wanna say hello?